Pile Foundation Modeler is the first product of LARSA's parametric modeling software suite. Utilizing LARSA's powerful Analytical Object Modeler technology, AOM in short. This tutorial demonstrates how a pile foundation can be modeled using AOM's parametric objects, such as pile caps, piles, and soil layers. And it shows how a detailed 3D finite element model is generated in real time before being exported to the LARSA 4D environment. When we open the Pile Foundation Modeler, an interactive guide welcomes us to start our modeling process. To begin, we click on the Go to Pile Foundations button. Here we can start by entering the parameters for our pile foundation. First, we click on Add Pile Foundation, enter a name such as PF1, and specify the location of the pile foundation. This location represents the center of the pile foundation model and should align with the piers it will be attached to in the LARSA 4D model. For this example, we enter the X direction as 160 feet, the Y direction is 0, and the depth is -40 feet. If needed, multiple pile foundations can be included in the same model, and all can be exported directly to LARSA 4D. Once we've entered the parameters, we click Update Model to proceed. Next, we define the pile cap by clicking Go to Pile Foundation under Pile Cap section. In the guide, we enter the pile cap thickness as 4 feet, the length as 25 feet, the width as 45 feet, and we select concrete with a 4 KSI compressive strength as the material. We then configure the piles by entering the pile depth as 32 feet and leaving the segment count as 8. Higher values allow for more refined discretization of piles. Next, we define the pile layout by clicking Add Pile Layout button, enter a name such as PL1, and select Piles in a rectangular grid as layout. Click Edit to set the grid dimensions. We begin with the starting corner at -6.5 feet in the X direction and -16 feet in the Y direction, and the opposite corner at 6.5 feet in the X direction and 16 feet in the Y direction. For the pile distribution, we specify 2 piles along the X direction and 5 piles along the Y direction. After entering these parameters, we click Update Model to apply the configuration. In the next section, we define the pile cross-section by clicking the Go to Pile section and Material button. We then select a circular confined section, set the outer diameter to 2 feet, and choose concrete with a 5 KSI compressive strength for the unconfined and confined materials. Finally, we specify grade 60 for the rebar and click Update Model to continue. Before defining the soil profile, we adjust the screen view for better visibility. Next, we click Go to Soil Profile button and begin by entering the water table depth as 37 feet. We then add the following soil layers: dry sand with a depth of 16 feet and a unit weight of 0.1 kips per cubic foot, soft clay with a depth of 21 feet and a unit weight of 0.1, saturated soft clay with a depth of 8 feet and a unit weight of 0.11, and rock with a depth of 20 feet and a unit weight of 0.14. After adding these layers, we click Update Model to apply the changes. At this point, the soil layers are defined, but the soil springs have not yet been created, as we have not entered the soil models. We proceed to define the soil models for each layer by clicking Go to Soil Model and selecting the appropriate models. For the dry sand, we use the Reese Sand Model for lateral soil model and the API Sand-Driven Pile Model for surface friction. For the soft clay, we select the API Soft Clay Model and the API Clay-Driven Pile Model for surface friction. Similarly, for the saturated soft clay, we use the API Soft Clay Model and the API Clay-Driven Pile Model for surface friction. For the rock, we use the Weak Rock and Florida Limestone models for lateral and surface friction soil models. After defining each soil model, we click Update Model. The springs for the piles are now visible in the analytical model. In the Project Explorer, we navigate to the pile foundations and select a pile. We check the nonlinear spring curves based on depth to ensure proper definition. After finishing the model creation, we have three options. First, we can perform an analysis directly within PFM. Loads can either be defined in PFM or extracted from an open LARSA 4D model. Second, we can export the entire pile foundation model as a 6x6 stiffness matrix to a LARSA 4D model. Lastly, we can export the full pile foundation model directly to a LARSA 4D project. This concludes our tutorial on the Pile Foundation Modeler. We hope you find this video helpful, and we invite you to contact us for more information. Thank you for watching, and stay tuned for future updates.